Okay, in part 3, what we're going to be looking at is magnetic forces, moving charged particles, and electric motors. So, electromagnetism is the combination or interaction of electric and magnetic effects. And two of the principles that we're studying, we just looked at one, which was that moving electric charges or current gives rise to magnetic fields. So moving electric charges create magnetic fields. And that is what creates an electromagnet. Now, the other possibility is that we're going to study in this one is what if you've already got a magnetic field and you send a moving charged particle through it or an electric current? That will deflect or push on the charged particle. And this is the basis for electric motors and generators. So these two together give us motors and generators. Okay, so let's go look at this deflection that occurs. So here we have a magnet, and let's say it's got a, maybe a north and a south. And so it's got a magnetic field moving across, right? Okay, from the north to the south. And the idea is, what if you had a current through a wire that is in that magnetic field? The interesting thing is when you turn on the current, there actually exists a force that will push it upwards if the current's going one direction. Or if the current is going the other direction, it might be pushed downwards. And you can already see that this could be a basis for an electric motor. You're making a wire go up and down if you can change the direction of the current. And that looks like some sort of machine. Now, the particles don't have to be in a wire. They can just be free moving particles. So a beam of electrons could move towards a magnet and they would be pushed upwards. Now, this is part of what's called the Lorentz force, which your book doesn't bring that name in when it's discussing this. On page 630 or something, but that is one of its names, the Lorentz force. It is perpendicular to the magnetic field and to the direction of motion of the charged particles. So the beam is one direction, like X, the magnetic field is another direction, maybe Y, and the force is a third direction, like Z, right? So 3 different directions for that. And so one thing that this means is that the electrons don't increase their velocity. Okay, they're pushed upwards, but they are not accelerated in the direction of the beam. So their velocity, or at least their speed, stays the same, but they are pushed in a different direction. Now, this picture is in your book, and this is a physicist using one of the right-hand rules here, where he's saying the force is equal to the charge that's being moved. This is the velocity of the charge, and this is the strength of the magnetic field. B represents magnetic field. So QVB. And he's got his thumb out because he's showing the direction, but here, behind him, what this is these are coils of wire with electricity through them. So there are 2 of them, and they're creating a strong magnetic field. And here is a beam of electrons coming out that is actually being curved around in a circle. So this is really a cool thing to do, where you can actually curve these electrons around in a circle or a spiral. Hi, Leo. You had a good walk? Okay, so moving charges in a magnetic field will experience a force, and those charges could be electric current in a wire, or they can be free. Okay. Okay, so how does this create an electric motor? So a motor is something that converts electrical energy into mechanical work. And so we were just looking with that wire that we were looking at that can go up and then down and up and then down. We were putting in electricity and we were getting out motion, right? Something was being forced for a distance. That's work. And so the idea is when we have a loop of coil that's carrying an electric current, Leo, go away, shoo shoo. A coil is carrying an electric current within a magnetic field. The coil experiences a force. Shoo shoo shoo. So here we've got a coil of wire. You put some current through it. And since it's in a magnetic field, it experiences a force. And that will actually make it rotate. And that's the basis for an electric motor. So the magnetic field, right, coming out of the north, going into the south, it's crossing this wire is in that magnetic field, and the current is flowing through the wire. So this wire experiences a force, and that force causes it to rotate. Okay, because it's fixed in place where that's all it can do is rotate. Okay, so anyway, so this is an electric motor. So we put in electricity and we got out rotation, mechanical work. Okay, so again, the current carrying wire experiences a torque. So it's fixed on a shaft, so it can't move except to rotate. And remember, the force is perpendicular to the magnetic field and perpendicular to the current. And it would be in different directions on the opposite sides of this wire, because you can think of the current going in this direction and out, oops, other way around, in this direction, out this direction. Okay, here these arrows show it. And so because of that, then the force is in opposite directions on the two sides. So that's why it rotates. Now, you can also think of this as, we were just talking about how a galvanometer worked. The coil of wire with electricity through it creates an electromagnet that can be repelled or attracted to a permanent magnet. And for a motor, though, we want it to keep moving, right? So a galvanometer, the needle just moves to a certain point and stops. How can we keep that going? And the idea is that you have to keep switching the current direction, because the electromagnet that you've created will get stuck in one position where the norths and the souths are lined to each other. And so what you have to do is you have to keep switching the current direction, which is easy with an AC current. With a DC current, so that current that only goes one direction, then what happens is you actually have what's called a split ring commutator. So the ends of the shaft are connected to this split ring, gets split in half here. And then what happens is, as it rotates, the shaft make contact with that ring, and one side is positive, one side's negative, but the shafts keep touching from the positive side to the negative side as they rotate. So that reverses the current every half cycle, and therefore that always keeps it so that the north is attracted to the south, but it never reaches it, because it switches once it gets over there. And now what was a north end becomes a south end of the electromagnet loop. So anyway, so it just keeps rotating. Okay, so that's the end of this part. So we'll talk more about motors and generators, of course, in the next chapter too. Okay, so we're going to go on to part 4. And let's stop.